Hello everyone, my name is Lola and welcome to my final presentation, Implementing Image and Video Super Resolution using ESPCM. So first, I'm going to talk about what is super resolution. Super resolution is recovering a high resolution image from a low resolution image. And since we're basing on a single image, it is also called single image super resolution. So how does super resolution work? We simply feed the low resolution image into a model, then we try to guess the high resolution image. In a traditional way, we apply mathematical method to calculate the equation to get the high resolution image. And now we have a new method using convolutional neural network as the model. So we apply the convolutional neural network model to guess the high resolution image, and we compare the difference between high resolution image from the model and the ground truth. Then we update the model every time. By doing this, the model will be trained again and again, and the performance will be better and better. So how do we compare the high resolution image guesses from the model and the ground truth? We use loss functions such as mean square error and the PSNR as a metric to evaluate. There are many different metrics to evaluate different super resolution image. In my implementation, I use PSNR as a metric since it is the most common metric that is used in super resolution. So what is ESPCM? The network of the ESPCM model assumes that there are L layers for the network, and the first L-1 layers, or convolutional layers, are obtained from the feature map of the low resolution image. And the last layer is a subpixel convolution layer to recover the output image size with a specific upscaled factor. So in my implementation, I had customized the dataset with a scaling factor of 3 and trained the model using 10 as the activate function with 200 epoch and compared the difference using PSNR. In ESPCM model, instead of using the deconvolutional layer to upscale the low resolution image, we come up with other way to upsample the layer. We add a new layer, the subpixel convolution layer, and we perform pixel shuffle. The general process of the pixel shuffle is a general convolutional operation followed by the rearrangement of pixels, which will rearrange the elements of a tensor of shape, so that the total of pixel is the same as a high resolution image to be obtained. And since the convolution operation are implemented on smaller size low resolution image, the efficiency is much higher. So I start with comparing between different models such as biqubit, ESPCM, EDSR. So the figure on the left is the original image, and the red box indicate the part that I'm trying to zoom in to test for different model. From the form below, we can see that EDSR is having the highest performance with the highest value for PSNR. However, the wait time is the highest at the same time, which means it's having a high computational cost. So after we finish evaluating different model, I use PSNR to evaluate our model, but is PSNR good for all our purpose? As we can see, it is not a fair game between an image that is all black or a colorful image. The PSNR will perform better in this black image since it is easy to train. However, if we implement on the colorful image, the PSNR will perform badly because it is harder to train. But we can't say if the PSNR for the colorful image is worse than the model for this is worse. Some images are easier to be super resolution, while some are not. So I add a baseline to help us evaluate our model, and the baseline is biqubit or bilinear interpolation. So now we try on different image set. The image set here I'm using mice and cat and Tom and Jerry because they are different objects but still mice and cat. And I'm using UAV crop as another image because viasat is a satellite company, so I'm using some high altitude image here. And here is some result running scale factor of 2 and 4. As we can see, most of the image do perform better than the baseline. For the scale factor of 4, there are 4 outstanding images that perform better. So we found these 4 images. Here are the first 2 images, and the third, and the fourth. The common things among these images is both these images are having more edges present. From the image good guy 4, we can see that the edge on after bicubic interpolation is jagged, and the one after model is smoother. And now we look into two images that perform worse than the baseline. We can observe that these images are more likely to lack of the variety of color, which they do not have a lot of edges and with huge amount of area with the same color. Finally, I also compared the performance between EDSR model and the ESPCN model. EDSR is having a better performance, but as the figure showed, ESPCN is more efficient than EDSR with only slightly difference on the performance. And the figure on the left is the image after EDSR model, and the right side is the one after ESPCN. EDSR has a smoother image, but the wait time is way longer than ESPCN. So to summarize, images are not equivalent to be upsampled, while some images are easier, such as the black image. And for most of the image, model perform better than the baseline. With the comparison of PSNR, we can conclude that the model is more likely to perform better on edges and bad on area lack of variation. And ESPCN model is a more efficient way among other models. And here are the reference of the paper. Thank you.